everyone. Welcome to First Principles. I'm Pradeep Vincent, SVP Chief Technical Architect at OCI. At OCI, we are opinionated about what makes a great cloud database experience. Customers should be able to add and remove database instances on demand, scale compute, scale storage, independent of each other. The service should be architected for zero recovery point objective and zero data loss so that the service is resilient to infrastructure level failures. The services should come with full automation so customers don't have to deal with mundane maintenance activities, and it should auto-tune to deliver the best performance at the lowest cost possible. We brought together Oracle's experience with database technology and OCI's experience in cloud scale services to deliver another world-class database in OCI Database with Postgres service. Joining me today to discuss the architecture of OCI Database Service with PostgreSQL is Vice President and Distinguished Engineer, Deepak Agarwal. Welcome, Deepak.
Thank you, Pradeep. It's great to be here.
Deepak has actually been with OCI pretty much from the early days of OCI. He led the architecture and implementation of OCI storage systems, network load balancing service, logging service, and most recently, the OCI database service with PostgreSQL. So Deepak, before we go into the architecture of OCI PostgreSQL, can we talk about how customers typically deploy and manage PostgreSQL database workloads in the cloud?
Certainly, Pradeep. I might sometimes refer to open source Postgres as vanilla Postgres. As you can see in this figure, a typical Postgres deployment includes at least 2 DB nodes in different fault domains for high availability. There's a primary database that allows read-write transactions and a read replica database. Now, before we go further, there are 2 fundamental concepts in databases that play a critical role across DB operations, such as commit and rollback, crash recovery, and replication. These are write-ahead log, or WAL, and log sequence number, or LSN. In Postgres, the WAL is a strictly ordered sequence of changes that have occurred in the database, and it is the source of truth. Records describing physical changes to a page are appended to the WAL before the page is written. And each record has a monotonically increasing number called the LSN. Database state can always be reconstructed by replaying the WAL. So one can replicate the DB by streaming the WAL from the primary to the read replica and replaying the WAL there. But customers face drawbacks, and there are some operational challenges with vanilla Postgres. First of all, replication between the nodes is asynchronous, resulting in a lag between the primary and the replicas. This replication lag is a major challenge. Because the replica must replay and persist all changes made by the primary, it is prone to falling behind, especially with network partitions. So there is some data loss in the event of primary failure. That is, recently committed transactions on the primary are lost. And the amount of data loss depends on how far behind the promoted replica was from the old primary, which can be arbitrarily large. Now, vanilla Postgres does offer synchronous replication, but it is not popular because of its significant performance overhead.
Got it. So essentially by default, you're saying the recovery point objective, or the RPO, is more than 0, is that right?
Yep. Moreover, promoting a replica to primary is a labor-intensive and error-prone process. A new primary has to be picked carefully to avoid data loss. And re-adding an old primary back into the cluster requires more manual steps. Notice that this setup requires at least 2 nodes. Even if the primary is enough for the workload, a read replica must be deployed for replication. This increases both compute and storage cost. Also, creating a new replica requires taking a snapshot of the data on the primary and replaying the WAL. For large terabyte-sized database, adding a new replica is an expensive and time-consuming operation.
I see. So essentially you're saying the vanilla PostgreSQL has its downsides with data loss during primary failover, and it has complexity around manual promotions and manageability. And creating read replicas looks like it's a pretty expensive and slow operation. So let's come back to OCI Database with Postgres. How do we solve all of these challenges with our service?
OCI Database with Postgres pushes the problem of replication and durability to a new database-optimized storage layer, which was purpose-built for high availability and high performance. It is a replicated shared storage system that allows single primary and multiple read replicas to share both the WAL and data. Now, because it uses quorum-based replication across multiple availability domains, it can survive the loss of an entire AD without any data loss. Primary failover is quick and almost transparent to the application with a recovery time objective of only a few minutes. The primary endpoint is set up as a floating IP that is automatically moved to the new primary, so the application settings don't need to be changed. Again, because the storage layer performs the replication, there is no need to run multiple replica instances just for the sake of durability. Customers can deploy a single node database instance without any replicas, and they're still guaranteed to have zero RPO even in the single node setup. And because all the replica nodes share the storage, you need to maintain only one copy of the database, regardless of the number of replicas in the cluster. The storage also auto-scales as data grows, so customers don't have to pre-provision storage. As a result, OCI Database with Postgres offers significant cost savings. Moreover, customers can create or delete replicas quickly to meet their workload demands. In fact, creating a read replica is as quick as launching a compute instance in OCI. With DB optimized storage, the replica does significantly less work when replaying the WAL. As a result, the lag between the primary and replica is typically in milliseconds, which allows the read queries to be executed in near real time. In fact, in our tests, OCI Database with Postgres with built-in replication across ADs was more than twice as fast as using synchronous replication in vanilla Postgres.
Got it. So essentially, the DB optimized storage used in OCI Database with Postgres offers several advantages: zero RPO replication, single elastic underlying storage across multiple replicas that saves cost, quick elastic creation of read replicas, and the replicas keep up with the master pretty closely. That's all great. Now, stepping back a bit, is the Oracle database with Postgres compatible with the vanilla Postgres? How easy is it to lift and shift your existing Postgres workloads to OCI?
Oh yes, it provides full Postgres compatibility and supports popular Postgres extensions as well.
That's awesome. So essentially, customers can lift and shift their apps very easily. So let's talk about the database optimized storage that you referred to.
Yeah, to run Postgres on top of DB optimized storage, we built a custom user mode file system. It exposes a single writer multi-reader access model to support a primary database and multiple read replica databases. Any changes to the file system made by the primary node are visible synchronously to the replica as soon as they are made. The file system is also LSN aware. By that, I mean both data and metadata changes in the file system are tagged with the database LSN. Unlike traditional file systems that treat blocks like opaque data, our file system tracks the LSN of individual database blocks. This allows Postgres read replicas to read a block at a specific LSN to achieve consistent read.
So you're saying that the WAL and the data are written directly to the database optimized storage. Is that right?
Yep.
So what exactly is communicated directly from node to node then?
The primary node exchanges only metadata with the read replica. It includes things like the LSN, active transaction IDs, and file system specific metadata. Replica reads the WAL and data pages directly from DB optimized storage using this metadata.
Got it. So how does the file system provide consistent reads for every database node on the cluster?
For the replica to satisfy a read query, it must be able to read the version of the page as of its current read LSN. By that I mean the page should have all the changes up to the read LSN and no new changes after that. This is critical when traversing index structures such as B-tree that might have concurrent structural modifications such as splits and merges. Reading a future page can lead to inconsistencies. So to allow a replica to read a page at specific LSN, the file system keeps multiple versions of the page at various LSNs. When the primary flushes a page, either as part of a checkpoint or cache eviction, it doesn't overwrite the previous versions. In a scheme similar to log-structured file systems, blocks are written to new offsets and multiple versions of the block are available to the read replica. Older versions are eventually discarded when the system determines that all replicas have moved past the LSN and the block is no longer needed. In this figure, the primary first persists block 0 at LSN 90 and subsequently at LSN 100. Because the replica is still at 90, the write with LSN 100 is persisted into a separate location. When replica makes a read request for the block, it gets the version at LSN 90.
Got it. So I can see how we achieve consistent reads when the read replica lags. That's great. But what happens when the database optimized storage lags the replica's current replay LSN? How does that work?
Right. Yeah, it is possible that the primary has not persisted the page as of the replica's read LSN. The process of flushing pages on primary is independent of replica's LSN. And in that case, the primary reads an old version of the page from the shared disk and on the fly replays any WAL records applicable to this page to bring the page to its current read LSN. To make the WAL replay efficient, each replica maintains an in-memory index of all the WAL records needed to reconstruct the page. In this figure, the primary has persisted block 0 at LSN 50, while the replica is at LSN 90. When the replica makes a read request for the block, DB optimized storage applies all WAL records between LSN 50 and 90 and then returns the page to the replica. Having the WAL index ensures that even if the primary has not persisted the data to storage, replica reads are still consistent.
So what happens when a primary fails? How do you address that problem?
Yeah, for high availability, OCI Database with Postgres automatically detects unhealthy primary instances and fails over either to an existing read replica or launches a new instance for single node deployments. The process of failover must ensure not only that the unhealthy primary stops making any new changes, but also that any in-flight I/O requests to shared storage are canceled. To handle these complex cases, it uses block layer NVMe reservation or SCSI-3 persistent reservation to fence out the old primary. This ensures that there is a single primary at any given time.
So far, we covered how database optimized storage architecture improves availability, durability, elasticity while saving costs. But how do we deliver on higher performance?
To deliver high performance, we made several optimizations specific to Postgres database in the storage layer. First, we built a caching layer in the file system that complements Postgres buffer cache. It has custom prefetching logic tailored for Postgres workloads. And it avoids double caching pages in Postgres buffer cache and file system cache, which improves performance. Second, we implemented atomic write for database pages in the storage layer. Now, typically, most database needs some sort of protection against torn writes. Torn writes happen when the database page size doesn't match the file system block size. So to avoid corruption, Postgres first writes an entire 8 KB page to the WAL when a page is modified after a checkpoint, and then flushes the page to disk. This results in a lot of extra IOs and overhead. We use log structuring technique to always write pages to new location on disk and maintain a mapping layer from logical file offset to disk location. This avoids double writes, improving performance.
That's awesome. Well, thank you, Deepak, for walking us through the architecture of OCI Database with PostgreSQL today.
Thank you for the opportunity, Pradeep.
We're always proud to innovate on behalf of our customers. Here are some key takeaways. Database optimized storage and the database optimized file system that are purpose-built for optimizing Postgres to work more effectively at cloud scale is a key bedrock of the OCI database service for Postgres. Database optimized storage automatically replicates data across a region with no data loss during primary failovers, essentially the zero RPO failovers. OCI Database for Postgres scales read workloads horizontally and enables high-performance, consistent reads across all replicas in the cluster. Database-optimized storage provides significant cost savings to customers because they don't actually have to replicate and store multiple copies of the data, and the storage is automatically scaled down when the data size reduces. Thank you for joining us today.